Okay, let's go ahead and get started. So, last time we left off in the middle of the proof of this theorem. So, let's just sort of remember where we were and finish this off. So, we were proving the following theorem. So, if G is a finite abelian group and P is a prime number that divides the order of G, then the theorem says that G has an element of that prime order P. Okay, and the way that we were going about proving this was by strong induction on the size of G. So we did the base case, and then we were in the middle of this inductive step. So for our inductive hypothesis, we assumed that whenever you had a group H with order less than that of G, if P is a prime that divides the order of H, then H has an element of order P. So that was our inductive hypothesis. Okay, so then we showed that G, in fact, had some element of order, of prime order, maybe not our favorite prime P, but of some prime order Q. So then, since the group is abelian, we know that we can take the quotient group, G mod the group generated by that element X of prime order Q. And this group, what is the order of this group? Well, it has to be the order of G divided by the order of the element X by Lagrange's theorem. So then this group G prime is a group of order smaller than G, and P is a prime that divides the order of G prime. So that means that G prime has an element of order P. So then what we're going to do is use this element of order P in G prime to construct an element of order P in G. Okay, so let's call, so G prime has an element of order P. Let's call it Y times that subgroup generated by X, because these are, so we're in the quotient group, so this is, elements of this are left cosets of the group generated by X. Okay, so what do we know? We know that the order of Y of this element is P, so let's find an element in the larger group G that also has order P. So to that end, I'm going to let L denote the order of the element Y in G. Then we can observe that if I take in G prime the element Yx and raise this to the L power, well, by properties of cosets, so just by the definition of coset multiplication, this is Y to the L times the subgroup generated by X. And since L is the order of Y, this is equal to the identity times the subgroup generated by X, which is just X. So we see that in G prime, raising this element to the Lth power gets me back to the identity element in G prime. So we must have that the order of this element divides that number that we raised it to get to the identity. And we'll recall that the order of this element Yx was P, so that means that P divides L, which was the order of Y. Then that means that Y to the L over P is an element of G with order P. And that completes the proof. Okay, are there questions about this? I know it's hard to pick back up in the middle of a proof. Yeah, do you have a question?
So in particular, the theorem says that all finite dimensions have an element sign.
Yeah. Mm-hmm. Yeah, other questions? Yeah. Okay, so what was the relevance of it being abelian? We needed that this was a normal subgroup. And so we know in an abelian group that every subgroup is normal, so that's where that hypothesis came in. But yeah, so you could wonder in what other settings is something like this true. Other questions? Okay, so now our topic for today is going to be something called group homomorphisms. So we've already dealt a lot with isomorphisms, and this is going to be like a relaxation of the isomorphism condition or a generalization of isomorphisms. And this will allow us to make maps between two different groups, and so we can compare different groups. So let me just give you the definition. So a homomorphism phi from a group G to a group G prime is a mapping that preserves the operation. Okay, so we have that phi of the product of two elements, A and B in G, is equal to phi of A times phi of B, where now this operation is taking place in the group G prime. Okay, so how is this different from an isomorphism? We're not asking that this is a bijection. We're just asking that it preserves the operation. Okay, and I'm going to give you an immediate sort of subgroup related to a homomorphism, and this should be somewhat familiar from linear algebra. So we'll say that the kernel of a homomorphism phi from G to G prime is the following set, and it's denoted ker phi. So this is the set of x's in G that are sent to the identity, so such that phi of x is equal to E. Okay, so that is the kernel. Okay, so let's see some examples. So isomorphisms are homomorphisms. What is the kernel if phi is an isomorphism? Yeah. Yeah, so the kernel is just the identity. So, of course, we're going to have that phi of the identity. If phi is a homomorphism, that is always going to be the identity in the group G prime. We already saw this for isomorphisms. And isomorphisms are injective, so the only thing that gets sent to the identity is the identity. So the kernel of an isomorphism is just the identity. Okay, are there questions? Yeah.
Sorry, mapping, do you mean it's a function?
Yeah. You can say function. Other questions? Okay, let's see another example. So let's consider phi from the integers to the integers mod n. Give me 1 second. Hey, can I have this? I don't think he got it. I don't think he consumed any of it. He was just holding on really tight. Thank you. Okay, so let's consider this homomorphism, or consider this map. So where phi of an integer m is equal to m mod n. Okay, so I'm going to give you a few minutes to think about whether this is a homomorphism. And what is the kernel? Hey, Bob. Okay, so let's see how this goes. So this map is a homomorphism, and this is just because if I take A mod n plus B mod n, and I mod this again by n, that is equal to doing a plus b and then modding by n. Okay, and you could see this by, if you wanted to, you could write out a and b in terms of like the remainder theorem and just check this, but this equality is true, so this map is a homomorphism. And then what is the kernel? So anything that's a multiple of n, when we mod it by n, will go to 0, which is the identity in Zn. So multiples of n is the kernel. So we have nz is the kernel of this phi. Okay, are there questions? Okay, so I'm going to give you a list of properties about homomorphisms, and some of these will be familiar from the properties about isomorphisms. So this is a theorem, and this is a list of properties about how elements in groups behave under homomorphisms, and then we'll get another theorem about how subgroups behave under homomorphisms. So let's let phi from G to G prime be a homomorphism. And let's let little g be an element of big G. Okay, then we have the following things. So phi of the identity in, and I'll just denote this with a subscript G so that we're not confused about which identity element I'm talking about. This is going to be equal to the identity element of the group G prime. 2, phi of the element G to the n is equal to first taking phi of G and then raising that to the nth power. And this is true if n is a positive or negative integer. 3, if the order of G is finite, then the order of phi of G divides the order of G. 4, the kernel of phi is a subgroup of G. 5, we have that phi of A is equal to phi of B if and only if the corresponding left cosets of the kernel are equal. And then the last property is that if phi of G is equal to G prime, then the set of x's in G that are also sent to G prime, this is equal to the left coset G cur phi. Okay, so I'm going to give you some time to think about and discuss how to prove these properties. And then if there are any that, that stick out that we want to go over, then we can talk about the proofs afterwards. Okay, are there ones of these that you all want to see proved? Any 5? Others? 5? Okay, I'm seeing 3 and 5. 6 also. Okay, yeah, these were the ones that I also identified as like maybe not being totally straightforward. So let's do these out. So okay, for 3. So how do we prove this? We will have to use like actually results that that we've proved. It's not, I think, like 100% straightforward from the definitions. So let's suppose n is equal to the order of g. So that means that g to the n is equal to the identity. So then phi of g to the n, well, this is also equal to the identity by the first 2 properties. Or sorry, maybe just by the first property. But this is also equal to phi of g raised to the n. So what that means is that the order of g has to, the order of phi of g has to divide this exponent. Right? Because if you raise an element to some power and you get the identity, then its order has to divide that power. Okay, so that was 3. Other questions? Okay, so for 5, this one is pretty quick actually if you use coset properties. So, and we won't even have to prove both directions because it'll just be a string of if and only if statements. So we have phi of A is equal to phi of B. This is true if and only if phi of A B inverse is equal to the identity. Is this step clear? This is like by property 2 of this theorem. So if I multiply both sides by phi of B inverse, then I get here. Okay, so that means, so this is true if and only if AB inverse is an element of the kernel of phi. And then we had a coset property that said that this was true if and only if the cosets A cur phi and B cur phi were equal. Okay, is it good? Okay, so then for 6, I had to prove both directions of this equality, so let me just pull this so that we have the statement. And we have that phi of g is equal to g prime. Okay, so let's prove both containments of this equality. So I'll start with this one. So let's just take an arbitrary element of g cur phi. So I'll just take g times h to be an element of the kernel of phi, of g kernel of phi. So h is understood here to be an element of the kernel. So that means that phi of GH is equal to phi of G, phi of H. The phi of H is sent to the identity, so this just leaves me with phi of G. And this was, by assumption, equal to G prime. So that means that, so that string of equalities tells me that GH is something that is mapped to G prime, so it's an element of the set on the left-hand side, which was what we needed to show for that containment. Is that clear? Yeah. H is in the kernel, so this is the identity. Yeah. Other questions? Okay, so then for the other containment, let's let X be an element of the set, so it has the property such that phi of X is equal to G prime, and then we want to show that it's in this coset. So we have that phi of G is equal to phi of X, and by this property, so number 5 of this theorem, so this next line is by part 5 of this theorem. This means that G times the kernel of phi is equal to X times the kernel of phi. So those two cosets are equal. And so that means, so since X is an element of this set, that means that X is also an element of G kernel phi. Okay, are there questions? Okay, so if not, there's going to be a second long theorem of a list of properties. So this is properties of subgroups and how they behave under homomorphisms. So for this, we'll let phi be a homomorphism from G to G prime. And let's let H be a subgroup of G. Okay, then we have the following. So the first one is that phi of H is a subgroup of G prime. The second says that H is cyclic or abelian or normal. I'm going to rephrase this. So if H has one of these properties, then phi of H has the same property. Okay, so if H is cyclic, phi of H is cyclic. If H is abelian, phi of H is abelian. If H is normal, phi of H is normal. And then the last property is that if the order of H is equal to n, then the order of phi of H divides n. Okay, so again, I'm going to give you a few minutes to think about how to prove these, and if we want to prove any of them together, then we can go over how to do that. Okay, so I have a typo in this, in number 2, which I realized because I tried to prove it and it felt impossible. So for the normal case, so let's delete this. For the normal case, if H is normal in G, then phi of H is normal in phi of G. Okay, so then if you, with the corrected statement, then the proof is straightforward. The problem that I was running into, and probably you were too if you were trying to prove this, is that if you just have like an arbitrary element of G prime, there's no way to know how it interacts with the target of phi. Okay, so I am going to not prove any of these so that we have time to get to like the main, so we can get through the main theorem of this section. But if you did get stuck on one of these proofs or you want to see how it goes, they are in the textbook. So I would recommend you to read it there. Okay, so here's a theorem. And this is going to be a precursor to something that we'll talk about next time called the first isomorphism theorem. So this says that we're going to let phi go from G to G prime be a homomorphism. Okay, then the kernel of phi is a normal subgroup of the group G. Okay, so whenever you have a normal subgroup, you might ask yourself, what is the quotient group G mod kernel phi? Because now this is something that we can look at, and this will be answered next time by the first isomorphism theorem. But for now, let's just prove that the kernel is normal, and then we'll see next time what this is. So for the proof, we need to show that for all elements A in the group G, we have that A times the kernel of phi times A inverse, that this is equal to the kernel of phi. And this will tell us that the kernel of phi is normal in G. So I'm going to do this by proving both inclusions. So I'll start with this one. So for this inclusion, let's let A inverse be an element of A kernel phi A inverse. So here H is going to be an element of the kernel of phi. Then we need to show that this element is in the kernel. So we want that A inverse is an element of the kernel of phi. So let's apply phi to it and see what happens. So we want that phi applied to A inverse, that is going to be the identity. Okay, so let's see how this goes. So I'm just going to separate this out using the definition of homomorphism. So we get phi of A, phi of H, phi of A inverse. And then since H was an element of the kernel, this is just phi of A times the identity in G prime times phi, and then by our properties from the other theorem, this is phi of A inverse. And then multiplying all of this out, we get the identity. Okay, so all of this implies that AHA inverse is an element of the kernel of phi. And that proves that one portion of that one containment. Okay, are there questions so far before we do the other containment? Okay, so let's do this other one. So let's let H be an element of the kernel of phi. Then what do we want to show? We want to show that H is an element of a kernel of phi A inverse. Okay, so by the above, I claim that we also have that A inverse HA is an element of the kernel of phi, just by repeating that same calculation from the previous part. And we can write H as follows. So H is equal to A inverse H A inverse. And I'm going to apply suggestive parentheses. Okay, so this is an element of the kernel of phi. So that means that this is an element of A kernel phi A inverse. Okay, and that proves that portion of the proof. And so we're done. Are there questions? Okay, so I'm going to start us off next time with another example of homomorphisms, just so you can get some more concrete pictures in your head of what those look like, and then we'll also talk about the first isomorphism theorem. So I'll see you on Friday.
That's just the range of field that's restricted. The main restricted state.
Yeah, it's just like, yeah, everything. You don't. You be barking. Yes. You don't.
that's
Can't
okay.
move this.
No. You're pretty efficient in engaging students at the end of class. No, I think you've gotten everything.
I stood in this unsheltered place till I could see the face behind the
Hey,
face.
Alan. How are you?
All that had gone before had left no trace.